Welcome to this fourth video in the DIDCOMM Superstack series. This fourth video focuses on Prototype 3. Prototype 3 builds on Prototype 2, where we saw how we can send a single DIDCOMM message to multiple recipients. Here we take that basic DIDCOMM messaging scenario and extend it to a higher layer, one level up, to support the VCTPS DIDCOMM protocol that you see illustrated in this sequence diagram. The scenario might be Alice wants to broadcast a request for quotation to multiple people, Bob, Carol, and Dave. But rather than just sending them the request for quotation, represented as a verifiable credential, she wants to check first with each of the recipients to make sure that they agree to the verifiable capability authorization rights, restrictions, and processing options she's set out. So Alice is going to send a notify message containing that VCA to Bob, Carol, and Dave. One or all of them, one or each of them, may choose to respond that they agree to confirm and accept the rights, limitations, rights, restrictions, and processing options in the VCA, and they respond with a pull message containing a VCA acknowledgement. The VCA acknowledgement contains a copy of the original VCA encoded in base 64 as one of its properties. Alice, on receiving that, inspects the pull message, inspects the VCA acknowledgement to see whether Bob has accepted the rights, restrictions, and processing options, and having done so, Alice is going to use a push message to send the VC to Bob. The VC is also going to have a base 64 encoded copy of the VCA for traceability purposes. So this is the transport level protocol message flow that we're going to see enacted in Prototype 3 on top of basic DIDCOMM messaging. So let's look at some source code. So here in the main line, we set up our key vault, again, just a simple in-memory key vault like we've done previously. We have some boilerplate JSON for the verifiable credential, the VCA, and the VCA acknowledgement that we're going to use. Normally, these would have to be created programmatically, and that the proper identifiers and whatnot would have to be set for the relationships between these three. But for this particular demonstration, we just basically need some boilerplate, some JSON payload. So let's start up the DIDCOMM agent. Again, we're just going to take an instance of our DIDCOMM agent implementation, and we're going to call start on that. This is the same DIDCOMM agent, unchanged from what we saw before in Prototype 1 and Prototype 2. So we define the server supporting this protocol. That protocol is realized as an endpoint. That endpoint accepts HTTP requests of the form DIDCOMM message and has DIDCOMM responses and up the chain here. So ultimately, what we want to receive is a DIDCOMM message, and in that DIDCOMM message is going to wrap an encrypted message, a DIDCOMM agent encrypted message. And it's really from that point on that this particular prototype gets interesting. What we actually do in Prototype 3, because we're still just for demo purposes running a single physical instance of the DIDCOMM agent, is that within the DIDCOMM agent, we have a series of message queues, one message queue for each of the recipient key IDs, indexed by each of the recipient key IDs. So every time we receive a new key ID, we create a new message queue. And so although there's only one physical endpoint that's being called, and all the messages are arriving through that one message point, regardless of the agent that they're destined to, they're going to be factored out into their individual message queues, and the encrypted messages, the encrypted messages will be stored on those queues for individualized processing. So before we get to that, let's just look at how we kick off again our VCTPS DIDCOMM protocol. We need to send a notify message. The recipients need to look at those, decide if they want to respond. If they respond, Alice will get a pull message, and then Alice will issue a push. So let's see how that works. So here we're going to send the notify message, and the notify message, in fact, all the VCTPS message factory methods return a core message. This is from the intrinsic DIDCOMM library. And an important thing to note here is that it's the core message itself that records who the originating key ID was and who the recipient key IDs are, or who the recipient agents or subjects are based on their key ID. So we're going to create that message. This is a one-to-many message that's going to be sent out, and we have the verifiable capability authorization JSON as attached to that as the payload. So we have a helper message. It sends a payload, a verifiable credential, from one key ID to another key ID. And it sends them via this particular DIDCOMM agent endpoint URL. So in this case, we're going to get 2 notify messages being sent off, and ultimately that's going to be received by our DIDCOMM endpoint handler. The agent, once it's started previously, it runs on its own thread. So we can send messages asynchronously to that DID agent. And then on the main thread here, we're going to continue polling the queues, the message queues, for each of the recipient key IDs, and processes the messages accordingly. Before we do that, let's just look at the DIDCOMM helper briefly. So it takes a URL, a from key, a to key, and the core message. It's going to call DIDCOMM pack from the intrinsic libraries to create an encrypted package based on the sender's secret key and the recipient's public key. And then we're going to take that encrypted message, the encrypted message property, out of the package, and we're going to use that to create a DIDCOMM agent encrypted message. And that's what we're doing here using the constructor. Again, this constructor is just based on the properties that were established up here for what an encrypted message looks like. Every one of these structures, when it's compiled by the Trinity compiler, Trinity code generator, generates a tightly typed C# class. So we can see that's what's happening here. So we've done that. We've created the message. Any Trinity message can be turned into a JSON string simply by using the toString method. So here's a JSON representation now of our encrypted message. And so we're going to call our send HTTP helper message to send that JSON to the endpoint URL. This send HTTP message just uses the ordinary HTTP class to post with the JSON payload as the body of the HTTP post request. So we're finished with those. So what happens then is each of those notify messages are initially going to come into our handler here. It's going to be received as a request. Remember the request, the DIDCOMM message that's defined in our TSL has an encrypted message property. So we're going to get the encrypted message. We're going to get a DIDCOMM encrypted message back. We're then going to use the intrinsic libraries to rebuild the encrypted message so that we can then process that internally on our message queues. So we're going to see if there's an existing message queue for the particular recipient key ID. And if there is, we're going to enqueue the message on the queue for that particular recipient key ID. If it isn't, we're going to create the queue first. We're going to return success and exit our DIDCOMM endpoint handler. Note that the DIDCOMM endpoint handler is very efficient in that it just does a little bit of data manipulation and tries to enqueue the encrypted messages as quickly as possible. We enqueue the encrypted messages, one, because we want to defer as much work as possible, and second, when we're passing these around, we want to leave them in a secure, private, encrypted format. And so the two notify messages will come in here as the message queue processing handles, for example, that notify message and generates pull messages and in turn generates push messages. All of those are going to be filtered and processed through here. So back here on the main thread, we have this loop, which again is polling the message queues. For every queue that's in the queues, while there's a non-zero number of messages, we're going to dequeue the message, and then we're going to process that encrypted message. So by processing that encrypted message, we need to find out who the sender was and who the recipient is. Those are properties in the header of the recipient message. And so we're going to use the recipient key and the sender key to look up the sender's public key and the recipient's secret key in the key vault, and we're going to unpack that message. We're going to decrypt that message and reconstruct the core message. And then we didn't look actually in the VCTPS message factory methods, but the way that they encode the verifiable credential is to take the JSON representation of that credential and store it as a text property of a basic message. And so in terms of the message layers, we have basic message layers, basic messages that wrap the actual JSON text of the credential. We have a core message which wraps that and provides basic DIDCOMM routing information. And then we encrypt that to create encrypted messages on top of that. So this is the processing that you see here. Finally, we end up with the text of the verifiable credential or the VCA or the VCA acknowledgement that we wanted to send in the first place. Because we're only dealing with VCTPS messages in this particular demo in prototype 3, we're simply going to call our process TPS message handler here. And this is where the actual protocol is implemented. This is where the transport level, DIDCOMM transport level protocol is handled. So if we receive an incoming notify message, Bob wants to reply with a pull message and an acknowledgement if he wants to confirm and accept the rights restrictions and processing options in the VCA. The VCA itself, when it's a notify message, is going to come through in this message parameter. So what Bob wants to do is create a pull message saying, yes, I want the VC. Here's my VCA acknowledgement. And he wants to send that from himself to the originator, to Alice or Charlie, whoever it might be. This is very key, that all of the routing is encoded in the core message. And by inspecting the outer properties of the core message, any piece of processing software can figure out the key of the source and the key of the recipient. So when it comes to sending a message from somewhere, we don't fool around by reversing the to and the from and the from and the to. We always take the properties of the pull message, for example, the to list, and the from, the singleton from key. And we always go from the from to the to. In this case, we're iterating over all of the key IDs in the to list, but there's only one key in the to list. So we're going to basically send this DIDCOMM message to the DIDCOMM URL from Bob to Charlie, and this will just be a single invocation of this message. So that gets us from the right side of the diagram back to the left. So here, Alice now wants to respond by sending a push message with the VCA. So when Alice or Charlie receives the pull message, they need to create a push message. They're going to create a push message with the VCA acknowledgement and the VC itself. They're going to get the key IDs right, the recipient and the source. And then we're going to do the same loop, the same mechanical loop, sending the pull message from a key ID to a particular key ID. Again, this will always be a singleton list. Not to worry. When that push message is sent, so the push message is going to go from Alice to Bob, and it arrives at Bob. Bob now has the verifiable credential. And so we have completed one iteration through the VCTPS DIDCOMM protocol. This is a transport level protocol. This is a secure transport level protocol. This is just to transfer a single verifiable credential. Again, the request for quotation. But this is going to be part of a higher level business process. The request for quotation is going to go out at a business process level, at the business application level, business architecture level. Needs to respond with a quotation, then a purchase order, and then perhaps a waybill, perhaps a delivery confirmation, and finally an invoice. But that's happening at a layer much above what we're seeing happening here. So that higher level business process, business rules, business application processing would happen in the workflow engine. So once we have the final VC, this is where we would call process the credential and pass that credential. In this particular example, it's just a placeholder. Ultimately, this will be replaced with a BPMN engine or some other business process level workflow engine. Okay, so we start off by generating 3 notifications up here, 2 notifications, 2 destinations. That kicks off the process. Everything is fielded by our DIDCOMM endpoint handler at the top. Based on what the recipient key is, we are going to sort those messages, partition those messages, so there's a queue for each recipient key ID, and their encrypted messages will be there. And then again, we've got this polling loop down here where we're going to just process those messages one at a time until that particular queue is empty. We'll process that encrypted message by decrypting it, by reconstructing the core message and the basic message to get the JSON text of the structured credential / verified credential. And then that we can now recognize as a VCTPS message. And we'll go through the process of notify from left to right, poll from right to left, and then push the verified credential from left to right, and ultimately drop it into our workflow process. So let's run that. Of course, it all happens very quick. So that's the there'll be 3 sets of these because it's set up with no business logic. So it just means that all 3 parties on the right are going to respond. And so we're going to be sending essentially 3 round trips, so 2 and 3, and then we're done. Now, what we see here is this is the endless loop of the polling, just in this particular example. Now, this I recognize as the final verified credential. It's actually a verifiable credential, a structured credential for a KISS. It just happens to be an example of some JSON for a structured credential for a non-fungible entity, and the non-fungible entity happens to be a KISS. We have a small Android app where you can kiss the screen and generate these credentials. So that's it. In the next prototype, we're going to begin using real credentials, and we're going to rely on the UBL schemas, the UBL business language for actual invoices and waybills and that sort of thing. Ultimately, in prototype 7, we're going to end up with a prototype that will implement this business workflow. ABC Grocery wants to order cabbages. There's 3 suppliers: Mary's Market Garden, David's Cabbages, and Paul's Produce. Quotations and purchase orders and all that are going to flow back and forth. Ultimately, a freight forwarder is going to be involved to create a waybill, bills of lading, transportation status events, delivery confirmations, and finally an invoice. Thank you for watching, and watch for the next video in the series.